The differences lesson will provide you with a general overview of operational differences between the 757 and the 767 airplanes. Now let's look at differences in the engines. The 757 is powered by two Rolls-Royce RB211 535E4B engines. Each engine produces approximately 43,100 pounds of takeoff thrust at sea level on a standard day. The 767-200 and 200ERs are powered by two General Electric or GE CF6-80A engines. Each engine is capable of developing 48,000 pounds of takeoff thrust at sea level on a standard day. The 767-300ER is powered by two General Electric CF6-80C2 engines. Each engine produces 61,500 pounds of takeoff thrust at sea level on a standard day. 757 and 767 ICAS displays are functionally identical, with differences involving the engine parameters displayed. General Electric exclusively uses N1 to measure primary engine thrust. Rolls-Royce uses EPR to measure primary engine thrust with N1 as an alternate measure. There is no EPR indication on the 767. The lower ICAS screen on the 757 displays N3. There is no N3 display on the 767 lower ICAS screen. The engine vibration indicators are also different between the two airplanes. As with ICAS, the 757 standby engine indicator provides EPR, N1, EGT, and N3 digital readouts. The 767 standby engine indicator provides N1, EGT, and N2 digital readouts. With both engines, start limits are referenced to a red line on the EGT indicator. The maximum starting EGT limit for the Rolls-Royce engine is 570 degrees Celsius. The maximum starting EGT limit for the GE engines is between 750 and 870 degrees Celsius. On both the 757 and the 767, down trimming of fuel flow is accomplished by an electronic engine control, or EEC. On the 757, EPR limiting is controlled by the EEC. On the 767, the EEC trims fuel flow for limiting N1 RPM. On the 757, the thrust control system also includes an electronic engine limiter control unit, or ELC. The purpose of the engine limiters is to prevent N1 or fan overspeed. The 767 GE engines are not equipped with engine limiter control units. The 757 does not have an amber reverser isolation light installed. However, the 767 does have an amber reverser isolation light installed. There are a few minor differences regarding the return to max climb power between airplanes. For example, the 757 can use reduced climb thrust throughout the airplane's operational envelope. On the 767, however, reduced climb thrust is terminated at 30,000 feet. Additionally, on the 757, selecting Climb 2 on the thrust rating panel prior to takeoff allows a special noise abatement profile. Let's now look at the fuel system differences. The fuel control switches for the 767 engine have only two positions, run and cutoff. The fuel control switches for the 757 engines have an added rich position. This position is used for fuel enrichment during cold engine starts, when the EGT indicates 0 degrees or less. On the 757, each main tank holds approximately 14,500 pounds of fuel. The center tank holds approximately 46,400 pounds, for a total fuel capacity of 75,500 pounds. On all 767s, each main tank holds approximately 40,700 pounds of fuel. The center tank on the 767-200 holds approximately 30,500 pounds for a total fuel capacity of 111,900 pounds. The center tank on the 767-200ER holds approximately 55,700 pounds for a total fuel capacity of 137,100 pounds. The center tank on the 767-300ER, however, holds approximately 80,400 pounds for a total fuel capacity of 161,800 pounds. The fuel configuration light and associated ICAS message will activate when fuel imbalance reaches 1,950 pounds in the 757. On the 767, the range is from 2,500 pounds at light fuel loads to 1,500 pounds at heavier fuel loads. On the 757, the fueling station is located on the right wing, and fuel temperature is taken in the right main tank. On the 767, the fueling station is located on the left wing, and fuel temperature is taken in the left main tank. Some 767-300ERs have a fuel jettison system. We'll now look at hydraulic system differences. On the 767, the center system provides hydraulic pressure to the flaps and slats, landing gear, nose wheel steering, and alternate brakes in addition to the primary flight controls and autopilot servos. The reserve brakes are also powered by the center system. The 757 and 767 hydraulic systems operate basically the same on both airplanes. Both airplanes have left and right engine-driven pumps and two center system electric pumps. The 757 has alternate action switches to control electric pumps for the left and right hydraulic systems. With on selected, these pumps run continuously. On is the normal position for flight. The 767 has three rotary selectors with off, auto, on positions which control three demand pumps. With the selectors in auto, the demand pumps provide system pressure when the primary pumps are not operating. They also supply additional pressure when system demand is high. In the on position, the demand pumps run continuously. Auto is the normal position for flight. The 757 has no auto function for the left and right electric pumps. Note the 757 has no air-driven pump as a backup on the center system. At the top of the hydraulic panel, notice the 757 has reservoir indicator lights, and the 767 has quantity indicator lights. The 757 reservoir light illuminates to indicate low reservoir quantity and/or low reservoir head pressure. The 767 quantity light illuminates to indicate low reservoir quantity. Head pressure to the reservoir is not monitored on the 767. The power transfer unit, or PTU, is a source of backup power for the 757 left hydraulic system. The 767 PTU provides backup power for the stabilizer trim if the left and center hydraulic systems fail. Let's look at the flight control differences, beginning with the ailerons. The 757 aileron system consists of a single outboard aileron on each wing. Each aileron is powered by two hydraulic systems. The 767 has inboard and outboard ailerons on each wing. Two hydraulic systems power each aileron. On the 767, to prevent overcontrolling at high speeds, an automatic aileron lockout system inhibits operation of the outboard ailerons and spoiler panels 4, 5, 8, and 9. At low air speeds, these ailerons and spoilers operate. The 757 has no aileron lockout system because the 757 has only one aileron on each wing. On the 767, the aileron lockout light illuminates on the overhead annunciator panel, and the aileron lockout advisory message appears to indicate a fault in the aileron lockout system. Should the light illuminate at low speed, the outboard ailerons may be locked out, or at high speed, the outboard ailerons may not be locked out. Aileron position is displayed on the ICAS status page. The 757 has only 2 pointers compared to 4 pointers displayed on the 767. On both the 757 and 767, when the autopilots are not engaged, the stabilizer may be controlled by the Mach speed trim system. The Mach speed trim system improves airplane stability by trimming the stabilizer as airspeed changes. Electric, alternate, or automatic trimming through the use of the autopilots inhibits the Mach speed trim system. The Mach speed trim light on the 757 illuminates, and the associated ICAS message appears, indicating a failure of the Mach speed trim system. There is no Mach speed trim light installed on the 767. Failure of the Mach speed trim system is not enunciated to the crew. The 767 has a pitch enhancement system, or PES, which provides backup for stabilizer operation using control wheel stabilizer trim switches if normal hydraulic sources fail. The PES operates automatically in the event of left and center hydraulic system failure. On the 757, two power drive units, or PDUs, are powered by the left hydraulic system. One PDU operates all leading edge slats, and a second PDU operates the trailing edge flaps. On the 767, three power drive units are powered by the center hydraulic system. One PDU operates the inboard leading edge slats. A second PDU operates the outboard slats. The third PDU operates the trailing edge flaps. On the 757, moving the flap lever from up to 1 provides takeoff slats, and the trailing edge flaps go to the flaps 1 position. On the 767, moving the flap lever from up to 1 only provides takeoff slats. The trailing edge flaps remain retracted. On both the 757 and 767, moving the flap lever to the 5, 15, or 20 detent extends the trailing edge flaps to the selected position. The leading edge slats will remain in the takeoff position on both airplanes. The only difference is that on the 767, the inboard ailerons droop in conjunction with flap extension. On both the 757 and 767-200 and 200ER, selecting flaps 30 arms the flap load relief system. If the selected flap airspeed limit is exceeded, the flap load relief system will automatically activate and retract the flaps to 25. As airspeed is reduced below the flap airspeed limit, the flaps return to 30. On the 767-300ER, selecting flaps 25 or 30 arms the flap load relief system. If the selected flap's airspeed limit is exceeded, the flap load relief system will automatically activate and retract the flaps to 20. The flaps will extend back to the selected position when the airspeed is reduced below the flap airspeed limit. Notice the differences in flap limit speeds posted around the flap position indicator. The 757 has an auto slat system that enhances airplane stall characteristics. Upon receiving a signal from the stall warning system, the slats automatically extend from the takeoff position to the fully extended landing position. The slats retract a few seconds after the signal is removed. The auto slat system is inoperative if the alternate flap and slat system is in use. The 767 does not have an auto slat system. The 757 has slat asymmetry protection using alternate flap operation. The 767 has no slat asymmetry protection in the alternate mode. Both the 757 and 767 have a control column shaker for stall warning. Only the 767 has a control column nudger. The nudger moves the column forward if the flap slats are in the retracted position, and the angle of attack continues to increase after a stall warning has been given. Another flight control difference is found on the accessory panel. There are 3 flight control shutoff switches on the 757 compared to 6 on the 767. They all have the same purpose. Both airplanes have switches to control the hydraulic shutoff valves for the rudder, stabilizer, and elevator. The 767 also has switches for wing shutoff valves for the spoilers and ailerons. The stabilizer trim position indicator green band takeoff range is different between the two airplanes. The 757 green band ranges between 2 and 7 units. The 767 green band ranges between 1/4 and 8 units. Now let's look at landing gear and brake differences. On the 757, the landing gear is powered by the left hydraulic system. On the 767, the landing gear is powered by the center hydraulic system. One difference that is not noticeable from the pilot's seats is the main landing gear tilt. On the 757, the main landing gear tilts aft when extended. The 767 main landing gear tilts forward. The 757 main gear is held up and locked by a main gear up lock. The main gear door actuator independently locks the main gear door up. On the 767, the main gear is held in the retracted position by the lock door structure. The 767-300ER has a retractable tail skid powered by the center hydraulic system. The tail skid is controlled by the landing gear lever. On the 757, normal and reserve brakes are powered by the right hydraulic system. Alternate brakes for the 757 are powered by the left hydraulic system. On the 767, alternate and reserve brakes are powered by the center hydraulic system. A switch on the forward instrument panel controls the reserve brakes on both the 757 and the 767. On the 757, the switch is labeled Reserve Brakes. On the 767, the switch is labeled Reserve Brakes and Steering. Although the switch is labeled differently, it's activated under the same conditions of hydraulic power loss to the brake system. Also on the 767, there is a Reserve Brakes and Steering switch and center hydraulic system isolation light located on the auxiliary panel. The norm position arms the isolation feature for automatic operation. The center hydraulic system isolation light illuminates when the number 1 hydraulic pump on the center hydraulic system is isolated. Let's look at ice and rain protection. The 757 wing anti-ice system heats the 3 mid-wing leading-edge slats on each wing. On the 767, however, the wing anti-ice system heats the 3 outboard leading-edge slats on each wing. Let's continue our discussion of differences by comparing pneumatic systems. Both airplanes use bleed air for air conditioning, pressurization, wing and engine anti-ice, engine starting, and hydraulic reservoir pressurization. Additionally, the 767 uses pneumatic air for cargo heat and the air-driven pump. The 767-300ER uses pneumatic air for the thrust reversers. On the bleed air control panel, notice the 757 has only 1 isolation valve. The 767 has 3. The 757 valve is located to isolate the right engine bleed air from the APU and the left bleed duct. The 767 has left, right, and center isolation valves. On the 767, the left engine normally supplies air to the left duct, and the right engine supplies air to the right duct. Both engines supply air to the center duct through a common manifold. A check valve on each side prevents the cross-flow of bleed air between engines. The center isolation switch on the 767 controls the flow of air into the center pneumatic duct. Bleed air overpressure is indicated by the high stage light on the 757 and the bleed light on the 767. Pneumatic high temperature conditions are indicated by the bleed light on the 757, the high stage light on the 767-200 and 200ER, and the overheat light on the 767-300ER. Continuing on, a duct leak light illuminates for the same reasons on both airplanes. The first difference to note is that the 757 has 2 indicator lights, whereas the 767 has 3, as shown. On the 757, a left or right bleed duct caution message will appear with the associated duct leak light. The 767 has body duct and strut duct caution messages in addition to the left or right bleed duct messages. Let's continue our discussion of differences by comparing air conditioning systems. On the 757, conditioned air is distributed to 3 zones in the airplane, so there are only 3 temperature selectors on the air conditioning panel, as shown. On the 767-200, conditioned air is also distributed to 3 zones in the airplane. Note that the flight deck temperature control has a manual position. There's also an associated flight deck trim air valve position indicator. On the 767-200ER and 300ER, conditioned air is distributed to 4 zones in the airplane, so there are 4 temperature selectors on the air conditioning panel. The mid-cabin zone temperature is controlled by the corresponding temperature selector. The flight deck temperature control and trim air valve position indicator are located on the lower portion of the air conditioning panel. Now let's discuss equipment cooling and cargo heat. Cargo compartment heating and ventilation is completely automatic on the 757. There are no cockpit controls or indicators except for ICAS status and maintenance messages. Each cargo compartment has a cargo heat fan that circulates cargo compartment air to even out the compartment temperatures. An electric heater provides supplemental heat to the aft cargo compartment. Let's now look at the 767 cargo heat. All 3 cargo bins on 767 airplanes are heated. Heat for these compartments is provided by cabin exhaust air and bleed air. The cabin exhaust air is ducted along the outside compartment walls and then discharged overboard through the pressurization outflow valve. Bleed air is ducted under the cargo compartment floor for additional heating. Cargo heating controls and indicators are located on the overhead panel. There are separate switches and overheat lights for each cargo compartment. When a cargo heat switch is selected on, the respective overheat valve opens and the heat control valve operates automatically to maintain the cargo compartment temperature above 45 degrees Fahrenheit. The 767 has a bulk cargo compartment heat selector located on the accessory panel. The selector has 2 positions, normal and vent. In the normal position, the temperature in the bulk cargo compartment is maintained above 45 degrees Fahrenheit. With the selector in vent, the compartment temperature is increased to a minimum of 65 degrees Fahrenheit. The equipment cooling panel on the 757 has an alternate action switch to select normal or alternate operation. The 767 equipment cooling panel has a 3-position selector, auto, standby, and override. The 767 auto position is the normal operating position for both ground and flight. Standby and override are used under specific conditions. The 767ERs have an equipment cooling monitor located on the auxiliary panel. Pushing the test bar up causes an indicating ball to appear in each tube. This indicates that cooling airflow is present to this equipment. Next, we'll discuss fire protection. 757's APU fire extinguishing system can be operated manually or automatically. For 757 APU automatic fire extinguishing, the airplane must be on the ground with both engines off and an APU fire sensed. The 767 has no automatic APU fire extinguishing. Although the APU will automatically shut down, the fire bottle must be manually discharged from the flight deck or the APU remote control panel. The 757, 767-200ER, and 767-300ER have 1 cargo fire bottle discharge switch. The 767-200 has 2 cargo fire bottle discharge switches. On the 767, smoke detection is provided in 3 cargo compartments. The 2 aft smoke detectors monitor both the aft and the bulk cargo compartments. The 757 has strut and turbine overheat detection. The 767 does not have turbine overheat detection. Strut overheat detection is only provided for the 767-300ER. However, it is not part of the fire overheat system. It's monitored by the pneumatic overheat system.